Hello, my lovely students. So we're going to take a look at this last crazy optimization problem. This one is going to involve angles. So we are going to be using some SOHCAHTOA stuff here. So we have, you are moving into a new apartment and notice there's a corner where the hallway narrows from 8 feet to 6 feet. What is the length of the longest item that can be carried horizontally around the corner? Okay. So when they say carried horizontally, what they mean is you can't do like top right to bottom left. Like it has to be level. You can't camp the angle to try to get a little more wiggle room. And my brain is like, this is literally pivoting. Didn't really watch Friends, but I saw that one scene. And yep, pivot. That's what we're gonna do. Hopefully some of y'all laughed. Ugh, straight lines. Now, when they say longest item, that's a bit of a misnomer here. Because we're not going to find the maximum length that we could try to squeeze in here. What we actually want to do is minimize the length because that's whatever the shortest length is. If I look at all the different lengths, if I wibble that L back and forth, rotate it, whatever the shortest L is, that is the longest object that I can put through that'll go through the entire turn, that'll make the pivot. So even though it says longest item, we are actually going to minimize the length. I'm calling it L just because they labeled it L in the figure. All right, so I drew in some right angles here because we actually need to talk about L itself. So let's put some right angles where they go. But absolutely down here, that's 8 feet. Over here is 6 feet. Now I need a way to relate my two constraints, the 8 and the 6, to the L. So, and we know we're going to be pivoting it. So when dealing with the pivot, what changes is the angle. Now, the interesting thing about the figure, or one of many, I suppose, I have two parallel lines. Here I am. I have two parallel lines being cut by a diagonal. Even though the lines themselves don't extend past, like we can sketch them in, and we see those two angles on the triangles are going to be the same. Even when L pivots, my 8 move up some, my 6 will move down the hall some as it pivots or vice versa. But those two angles will stay the same. They're equal to each other. What size they are will change, but the fact that they are equal to each other will remain the same. All right, so I'm going to label that theta on both of them. And then each of those sides, each of those little right triangles now, relates to one part of my overall length. So I need letters for the two parts of the length. I don't care what, so I'm just going to go A and B. So I'm trying to minimize L. And since I labeled pieces, right now my L is A plus B. So A is the hypotenuse of the triangle with 8 feet as a side. B is the hypotenuse of the triangle with 6 feet as a side. Now, in one of the triangles, our measured side is opposite, and in the other one, the measured side is the adjacent side. But in both cases, we need to relate this back to the hypotenuse. So down here, when I'm looking at my theta, I have opposite would be over here. A hypotenuse is across from the 90. So that means down here, 8 is the adjacent side. So we need something that relates hypotenuse and adjacent. That is cosine. So one of my new statements is that the cosine of theta is 8 over A. Well, hey, I can use that to change A into something in terms of theta. Because we're going to do the same thing up there with B, except now our 6 is opposite the angle. The unknown side we don't care about is the adjacent, and B is the hypotenuse, so now we're going to use sine. The sine of that same angle measure is 6 over B. So I'm going to solve those for A and B respectively, which we end up multiplying by the variable and then dividing by the trig function. So over here, B is 6 over the sine of theta. And back here, A is 8 over the cosine of theta. So now I can rewrite L as 8 over the cosine of theta plus 6 over the sine of theta. That is now an equation all in terms of one variable, theta. So now we are at the take the derivative, set it equal to 0 step. And take a breath and take a look at that and kind of go, well, we're either doing quotient rule, a very ugly to look at chain rule, or we trade these out for their reciprocal functions and go look up our trig rules. They all arrive at the same thing. It's just the amount of work it takes to get there. I'm actually going to opt for the third option because this is a homework question, not a test question. So cosine, the reciprocal of cosine is secant. So since this cosine is on the bottom, I can write this as 8 secant theta plus 6. The reciprocal of sine is cosecant. So with sine on the bottom, I can rewrite that as cosecant on top. So that is what L equals in terms of trig functions with no quotients. So I'm doing it this way because we could look up these formulas and then you're not having to run through the quotient rule with sine or cosine in it. I know you guys could do it, but that's just a whole lot of extra time that, why bother? So now our derivative. So the 8 comes down. And so the derivative of tangent, you end up with secant squared. The derivative of secant, you get secant and tangent, the product of them. So our derivative on this one is secant theta, tangent theta. And I just went through it that way because that's the way my brain remembers it. And then cosecant theta is going to be very similar to secant. So we're going to see the cosecant and the cotangent. But because we're dealing with a c function and we're taking a derivative, we get a minus. So there is our ridiculous derivative. And now we can set it equal to 0. It is a crazy equation all in terms of theta. It can be solved. You're going to not really like yourself, but we can do it. So what I'm going to do here is I'm going to write these in terms of sine and cosine because dealing with this mess is like, no, thank you. So secant is 1 over cosine theta. Tangent is sine theta over cosine theta. This is no longer a plus because that minus sign, this is now minus 6, 1 over sine theta. And then cotangent is cosine theta over sine theta. So it looks like I'm going to have cosine squared and sine squared in the denominators of these two. I really, truly hate fractions. We don't want to consider when sine or cosine is 0, because that means the angle is either 0 degrees or 90 degrees, both of which are the ridiculous end case scenarios. So I'm going to multiply by cosine squared and sine squared on both sides. Now on the left, it's being multiplied to the 0, so haha, it goes away. On the right, I'm going to have 8. And so this sine squared cosine squared is going to get distributed to both of these ridiculous products. So I've got a cosine squared on the bottom here. That will cancel out the cosine squared that gets distributed. So it leaves us with the sine squared times the resulting sine that's on top. So that is sine cubed theta minus 6. And then similarly, the sine squared that's on the bottom here would cancel the sine squared that's getting distributed in, leaving the cosine squared. So this will be cosine cubed. So this is where things get a little weird. So once upon a time, long, long ago, at some point, you probably saw the formula for the sum or the difference of cubes. Again, this is a homework question. This is not a test question. You are not going to have to do cubes, sum or difference of cubes on a test. This is more of a just somewhere in your history, I want you to recall that, yeah, you probably saw this. All right, so over here, if I have a cubed plus b cubed, that factors into a plus b times the square of a, the opposite sign, the pair, plus the square. It's the way I taught it in college algebra at the Alamo colleges way back in the day, so that's still how I remember it. Square, opposite pair, plus square. SOPs. Or same opposite pair. But whatever we start with, a cubed plus b cubed, this is a plus, this is a minus, the last one is always a plus. If we are looking at minus, this is a minus, this is a plus, and the last one is always a plus. So over here, well, I've got a sine cubed and a cosine cubed. Over here, though, it's just a cubed and b cubed. In mine, I've got that 8 and that 6, and they're kind of creating a problem. But we can handle them. We just got to get a little more creative. So if I want to write this as an a cubed times a b cubed, I'm going to have to figure out 8 to what power, then to the third power equals 8. So basically 8 is equal to the cube root of 8 cubed. So our 8 sine cubed theta, I can write that instead, and then I can write it all as the cube root of 8 times the sine of theta, and then that whole thing cubed. So there is our A ugly cubed. Minus, we're going to do the same thing with the 6. The cube root of 6 times just the cosine of theta cubed. So we can follow our results. And the interesting thing about the sum or the difference of squares is that this guy here never produces real solutions. So when we're solving a real problem here, when we do the sum or the difference of cubes, the only factor we actually care about is the front one that's like just singles. The other guy never factors into real solutions. It doesn't matter what A and B are. That format, if I plug in 1, -1, and 1 as my coefficients into the quadratic formula, you get an imaginary. So even though there's some numbers over here, it doesn't matter. It's imaginary. So for completion's sake, I'm going to actually write the fully factored form, but realistically, we were going to chuck out that second part right away. So there's my A, just to make it a little clearer, the cube root of 8 times the sine of theta. And some of you guys are probably going like, the cube root of 8 is 2. You want to write 2, you go ahead and write 2. But on your homework, they ain't going to be pretty. Maybe you'll get an 8, probably you won't. for sure, whatever your b is not going to be pretty. All right. Our original form had a minus, so we're going to have a minus in here. So a, that cube root of 8 sine theta minus the cube root of 6 cosine theta. That's one part of our factoring. And then the other part is a squared plus that's a and b rearranged and squeezed together plus no real solution, so we check that out and ignore it. So all we got to focus on is this front one here. So if a minus b equals 0, then what we're really solving here is a equals b. So the cube root of 8 times the sine of theta equals the cube root of 6 times the cosine of theta. All of this is just to try to find a critical value. All right, so if I have sine over cosine, I can trade that out for tangent. So I'm going to divide both sides by cosine. And since I'm going to trade that out for tangent, I want that cube root of 8 to not be on that side anymore. So I'm also going to divide by it on both sides. So I now have just the tangent of theta is equal to the cube root of 6 over the cube root of 8, which we could actually write as the cube root of 6/8, which does reduce to 3/4, whatever. So what we're going to do next is apply the inverse tangent. To both sides. Now, when you go to type this craziness in, you're going to have tangent inverse, and it opens a set of parentheses. Open another set of parentheses. We're going to do the 6/8 raised to the 1/3 power. So that's where I merged the quotient into the radical of the fraction. I'm not going to bother reducing it because whatever you guys get on your test isn't going to reduce more than likely. And it doesn't matter that the cube root of 8 is 2. Now I've got it all inside the cube root, so whatever. And also, I don't even really care what the cube root of that is. I care what the inverse tangent of the cube root of that is. So there's my inverse tangent. Open another set. 6/8. Close the set. Raise to the 1 divided by 3. Close. Now here, our question was, what is the minimum length? So theta itself, we don't actually care what the answer is. So we don't really care if it's in degrees or radians, as long as we stay in the same mode for the whole problem. So my calculator defaults to degrees, so I'm just going to go with the degrees answer. So theta is 42.25703 blah, blah, blah degrees. Cool. That's a number. Now we rewind a whole lot and we come all the way back to our original function. And we say, oh, well, I have a theta. If I put the theta back into the original function, that will give me an L, and that L should be the minimum. Now, it does always beg the question, how do you know it's the minimum? And usually the answer is, well, if you take a look at the graph, it's a minimum. So you could first derivative test, plug in like 40 degrees, see if the first derivative is positive or negative, Plug in 45 degrees. See if the first derivative is positive or negative. Yeah, you can. It's just annoying. But if it was like a polynomial, you could easily answer the how do you know it's a max or how do you know it's a min? Hint, hint, nudge, nudge, wink, wink. All right, so we're taking this guy back to L, which I'm going to write over here. L is 8 secant theta plus 6 cosecant theta. So L is 8. Now, for the purposes of typing on the calculator, my calculator don't give me secant and cosecant. So I'm just going to write 1 over cosine of 42.257, blah, 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 plus 6 times 1 over sine of 42.257, blah, blah, blah. Okay. 8 divided by the cosine of that angle, close, plus 6 divided by the sine of that angle. I say that because I was actually going back and picking the angle twice. And we get 19.7313, blah, blah, blah. So now I rewind a little more where they're units. Feet. The 6 and the 8 are feet. So that means our ridiculous 19.7 is feet. So the longest object we could take and pivot around the corner is a little under 20 feet long. That's just going by length. This is not accounting for the width of the object messing with the pivoting turn, because it would have an impact. It would actually shift these answers some, but that calculation is a lot more crazy. And the hallways are not the narrowing point. The real problem is the door into the apartment. That pivot is the one that is much smaller, because the doorway is not 6 feet wide. But in the general sense, like, this is the kind of calculation you could do if you had like a factory layout and you knew the factory was going to commonly like move items that were like 20 feet on the longest diagonal. So you could calculate, all right, if that 20-foot thing and the 2 people carrying it like move through here, are they going to have enough room to maneuver? Like, this is the kind of stuff. Usually what happens is a mathematician crunches the numbers and lays out some guidelines for people who write up floor plans and says, make sure all the hallways are this wide. And then somewhere in there, somebody cuts costs and says, well, if we just did this, and they never get back to the mathematician for the mathematician to go, nope, you can't carry the thing down the hallway now, you schmuck. But there is our answer. There is our solution. Again, this is very similar to web work number 3. On that one, it says a cable. It is lying. Cables are flexible. It doesn't want this thing to be flexible. It means like a conduit or a ladder. So think of it as a fixed length that's got to lean on a short wall and still reach across a building that's a fixed distance away. So the diagram is going to look very similar. You're going to see the 2 right triangles in there. Like, all the work is very similar. All right. There is like one last everything on one page.